are back today, and we are going to use our chi-square distribution to figure out and answer the question, are my rolling velocities normally distributed? So we've done several examples of chi-square, looking at basically coin flipping, heads or tails, random number generators. You could do rock, paper, scissors. We looked at different kind of dice probabilities of summing to different values, 2, 3, 4, 5, 6, all the way to 12. So we've looked at scenarios where the frequencies are same, or the frequencies are different, or are basically our observed values match what we expected from probabilities. But now we're going to answer the question, does my data set fit some type of distribution? It could be a normal distribution, it could be an exponential distribution, it could be a Poisson distribution, a Weibull distribution, whatever you're dealing with. So hopefully you remember back to the discussion that our degrees of freedom in our chi-squared hypothesis testing procedure are k minus 1 minus r, where r is our fitting number of fitting parameters, our degrees of freedom. So we're asking if our data is normally distributed. We know from our Gaussian equation, our normal distribution, that x minus mu squared over sigma squared. So our two fitting parameters r is going to equal, we have one fitting parameter in sigma, or standard deviation, and mu. So r is going to equal 2 in this scenario. So let's look at what this question is asking. So we need to go back to our data set and see if our rolling parameters, rolling velocities are normally distributed. So if you remember back, our sample mean, so our x bar of our means was 2.938. Sample standard deviation of our means, S sub x, was 0.367. And our n number of samples was 138. So it says here that we found that there are 15 measurements with velocity greater than 3.4, 43 measurements less than 2.8, and 27 measurements between 2.2 and 2.8. And then finally, ignore this, there's a typo here. I've updated that in the notes. There are 136 measurements between 2 and 4. But whenever we're doing a chi-square test, we have our observed values and we have our expected values. So for rolling velocities that are greater than 3.4, we find, or we observe 15 measurements. For less than 2.8, we find that there are 27 measurements observed. We find, 43. Okay, type up there. We find that there are 43 measurements less than 2.8. So here, we find that there are 27 between 2.2 and 2.8. So 27. And then finally, we find that there are 136 measurements between 2 and 4. 36. So we have all of our observed values. Now we need to figure out what our expected values are. So will these all occur with the same probability? No, we need to kind of see again, is this data normally distributed? So we need to go back and assume, okay, this data is normally distributed. We have a large sample size. So we're going to figure out how many data points should be greater than 3.4 based on our z-tables. So, and again, we're working at a 5% significance level, and we'll go back to our hypothesis testing later. So to find out how many samples, what's the expected samples greater than 3.4, I know that I know my x bar is 2.98, so this value is z of 0. You can see here my z calculation for 3.4, plugging in everything, is 1.23. So I know the area of z equal to 1.23. So 1.23 is 0.3907. So 0.3907, as you see right here, is the area from 0 to 1.23. I'm looking for the number of samples greater than 3.4. So that's just going to be, I know the area of this curve from z equals 0 to z equals infinity is equal to, that area is 0.5. So if I want this area, everything greater than 3.4, it's going to be 0.5 minus 3.907, and that will give me that area. And then to get my number of expected samples, I just multiply by n. So then that is going to be 138. So going back up here, my expected values match it here, 15. So far, so good. Less than 2.8, very similar procedure. So let's see where I fall on my curve here. So if I want to look at just less than 2.8, we can just, here's my value of z equals 0. My value from 0 to 2.8 is going to be what? Well, as you can see here, that z value is minus 0.37. So if I want every value less than 2.8, all I'm going to have to do is go to 0.3.7, 0.3.7, 1.433. So as you can see back here, this area in here is from z equals 0 to 0.37 is 1.433. So if I want everything less than 2.8, I'm going to do the same thing. 0.5 minus 0.143. And you can see that back up here as well. So 0.5 minus everything less than this probability here, multiplied by the number of samples. So my expected number is 49.1. So then the question asks between 2.2 and 2.8. So you do the same procedure again. I have my, you could see this picture here. We know the area from z equals 0 to 2.8. We just calculated that out previously. It's this value here. Now we could also figure out what's the area from z equals 0 to a z value of 2.2. You calculate your value of 2.2. You see this is 1.96. So we should hopefully remember that. Don't even have to look at the table. That's our 95% confidence interval. So if we're looking at half of our equation, that's just going to be 0.475. So the total area from here to here is 0.475, but I want the area from in this cyan area, so I need to subtract that area from 0 to 2.8. So once I have that, that's my area multiplied by n, and you can see that expected value is 45.6. So 45.6, very different. And then finally, we're asked between 2 and 4 for z value. So here I'm going across my boundary. So I need to first find, okay, what is the z value associated with 2? So I could see, okay, that's a z value of 2.498. So let's go back to our 2.498. Actually, let's go back. Let's see. 2.49, just to round it up. 2.49, so 4.936. Let's double check that. Oops. It doesn't like us. So between here and here, 0.4396. A z value of 4 is equal to 2.82. Let's go 4.9, 2.82. Let's go back 2.82 now. 2.3, excuse me, 2.49. Let's double check that. Yep, 2.49, and then 2.82, 2.82, 2.8012, 0.4976. So let's go back here. That sounds good. So that's the area from here to here. Is this area, the area from here to here, this area. So the total area, about 0.99, multiply it out, it's 137.6. 136.7, excuse me. So let's look at that. You can kind of see that value right here. So that's the value between that 2 and 4. 137.6. 36.7. I don't know why I keep saying that. Excuse me, students. So anyways, so I have all my observed values. I have my expected values. So how many number of outcomes, or how many number of variables am I possibly comparing? Well, I'm varying 1, 2, 3, 4. So k is equal to 4 here. So 4 minus 1 minus 2 is what? Nu of 1. So let's go back and let's look at how we do our, again, we are doing the same. We could actually say instead of frequencies that are the same, this is equivalent to saying normally distributed. And we just had k was equal to 4. So our nu is equal to 4 minus 1 minus the number of fitting parameters was 2 for our Gaussian distribution. So our nu is 1. Our confidence interval alpha was 0.05. It can never be alpha over 2 because we're using a chi-squared test. So normally distributed, frequencies are the same, frequencies are different, not normally distributed. So we are going to calculate out right now those values. So we have 1, 2, 3. We know our alpha is equal to 0.05. 4, we need to calculate out chi-experimental, which we'll show in just a second. 5, our chi-squared, we know that it's the alpha, 0.05. Value of 1. Let's go to our table. Chi-squared 05. 05, 1 is 3.841, as we can confirm here. Sorry about that. 3.841. So let's calculate our chi-squared. So if I look at my values, I have my, just calculating everything out here. So these are my counting. There's my z values. I'm going to get my area 1 times the length of my data set, my area 2. This is just kind of going through all the same math, plugging and chugging in, defining all my variables here. We said we saw, oh, excuse me, 37 between there. That's another typo. Excuse me, students. I'm going to have to rewrite this problem. So anyways, here we go. Let's rewrite that there. 27. It is 37. So 37 in here. So we will go ahead and if you look back down here, so that's our expected value, our reserve values. So let's actually show those out. Expected, just like we looked at it here, reserved right here, 15, 43, 36. Let's just compare them and make sure our tables look similar. So our expected values, 15, approximately 49, 45.6, 136.7. Our observed 15, 43, again, apologies for that, 37, not 27. And we'll go ahead and calculate it out. I see that my chi-square experimental is this, and we end up getting a value of 2.4, as we can see below here. And so we see, where does that fall? Let's go back to our hypothesis testing presentation. So if we have a right tail test, we see that our chi-square experimental was less than, so it falls in the do not reject region. So we are not rejecting our H naught, our initial hypothesis that what? That we were, frequencies were the same, that we were normally distributed. So this does indeed come from, or it seems to be, again, we're not going to get into the statistics talk, but that is what we're kind of doing here. So that's how you can run and do these hypothesis testing. Let's see, just for play around, I'm going to change my observe 1, observe 3. I'm going to change it, or expected 3. I'm going to change this to 27. We can see how the value, let's see what happens to our chi-square experimental. You can see here, now we're at 4.4, and we'd be in the reject region. Because again, we reject H naught, they are not the same, they are not normally distributed. So, accept the null hypothesis. So again, your answer could definitely change depending on what you observe in your data set. So remember, this whole chi-squared is a goodness of fit test. So one way you could kind of basically check, or usually again when we say a data set is Gaussian, we kind of just do an eye check. So there's no real figure of merit or kind of confidence interval or anything that kind of says whether something is normally distributed or not. But you can use use this goodness of fit, use this chi-squared experimental test. But it gets a little bit more complicated. There's a little bit of data manipulation. It's hard, especially for small samples. So there's some limitation to kind of this technique. You could still kind of use this. And again, most of the data that you'll find, even the populations, are going to be normally or Gaussianly distributed. But one of the key examples that we've kind of talked about a little bit is fatigue strength data. It is really well approximated using a Weibull distribution. So chi-squared is a nice experimental procedure where you can at least kind of, if you're not if the eye test, is not accepted, or if you really want to kind of dive deeper into your data set and give some kind of quantitative answer as to whether your data set is Gaussian or not Gaussian, the chi-squared test could possibly be a nice one for you to utilize. So, yeah, that's how you can see if your data is normally distributed or not. So use the z-values, calculate your expected values. Again, apologies for that the typo there. I'll fix that notes and repost on our Canvas site. And yeah, other than that, let me know if you have any questions. You can see, again, if you change that data set to 27, we'd be in the reject region. If it's back to its expected 3 value, which is what I actually calculated in the Mathematica notebook, you'll see that we get in that in the do not reject region. So our data is normally distributed. So yeah, that's about it for lecture 4. So on to lecture 5, propagating air. A little bit more math heavy, but it should be a fun lecture. So and a very useful one for your exams and also for your labs. So I'll see you on the next time, and let me know if you have any questions. Have a good day. Stay safe. and I'll see you all very soon. Let me know if you have any questions, and then yeah, have a great one. Bye.